sequence of diagram. The rest everything you can manage very clearly. This is the block M. It is compressed so that here spring force kx naught will act, and the block B is still at rest. BAC. We'll just try to see what all conditions will exist. So spring force will act. So the spring force what will happen? Will act till where? Till when it attains natural length. So when it attains natural length, somewhere here, it is natural. I'll spring is relaxed. So this will acquire velocity, say V naught. This will acquire velocity, say VA1, or we'll write VC1. Afterwards, it lose contact. Spring is relaxed, no? This is very important. Keep it here like this. So there's a block A. And what it will do, it will go and compress this particular thing. What is the state of block B? It is at rest, rest, rest. What happened to A1? This will continuously try to move. Now this will go and will, the moment it goes, the block C will goes and strike the spring. Spring what happened will get compressed due to compressive force. Due to compression, spring force will act on this towards left. Spring force will act on towards right, and both will have maximum compression. Let's analyze what all can happen so that we can conclude here. So this will continue to move. This will go and strike. Maximum compression occurs. I needed to show all striking, then that one, or one diagram. We'll put it. Where they'll be in compression. What will happen to velocity of the block? This will start decreasing, and this will be increasing. VB2, let me write it. VC will. So this will be under compression, no? KX, KX2, I'll write it. Then maximum compression will occur. Both will have common velocity. Because we are just searching what will happen. Both will have common velocity. Then again at one particular point, in what particular point maximum compression it is. So XM maximum compression. Then afterwards it will start coming out of there's a compression, maximum again compression, then again natural length will come. Close. Okay, now you say this. Okay, let's get into the maximum compression. Here only compression. Some X3, I'll write it. KX3, KX3. this will have velocity, say like a VB3. This will have velocity VC3. It's a compression still. Then at one position, they will have natural length. At one position, it will acquire natural length. Spring is relaxed. By this time, this will acquire some velocity, VB. This will acquire some velocity, VC. Then they will lose contact. This is the final condition that is taking place. So what is our question? Our question asked about finally. You can really, this problem, you can solve without drawing all these diagrams also. He's asking that find the speeds eventually acquired by A and B. The question is about testing your basic fundamentals, nothing to do with any concept. The diagram speaks a lot. So how you apply all the things, this one, this is the final. Okay, no. So what is the only condition available? M very much less than capital M. Is this correct, first of all? Anybody? So this is what happens or some other thing happens? Or is it only one time the block will come in contact with the block B? Or now only after this again, this will never come here? Unless you don't think this, say, this is what naturally we'll try to think. Oh, okay, this what. But try to take help of this from the beginning only, then only you'll be on safer side, otherwise gone. You cannot think just plain way like this here. You should think from the beginning. This M will be very much less than M. The moment I release, tell me which will have more velocity. VC1 will be very much greater than VA1. Any reason? This is thing. So your question should actually, this condition, if you start thinking in the end, no, then gone. It should be brought in the beginning only. So what is the basic idea? M is very much less than capital M. So therefore, VC1 will be very much greater than VA1. If you don't analyze this and just keep on draw diagram, you'll become artist. You'll not become engineer. Okay, like your teacher is showing diagrams. No? Anybody can draw. What is there in this one? We have to take that help of that condition. So VC1 will be very much greater. So this VA1 will be very less. So this will go now collide with this. Again, as VC1 is very much greater, it will impart some momentum. It will impart some momentum. Then it will return back. It will go and collide. Like that, the block, see what happened, will have n number of collisions. And finally, it come to rest. Since masses are same, they must have same velocity. I think the idea of the problem is like this. Actually, VC1 very much greater. Of course, so this will moving with a less speed. This will go collide. Again, will return back. It cannot be like this. It will be like this. Because this is a lighter mass. It will rebound. It is having very much high velocity. Again, will come and collide. Again, the sequence will be like that. The block, see what will happen continuously. Sequence will collide with first with B, then A, then B, then A. Finally, it will come to rest. Since what is the net force acting on system? Zero. Momentum should become the initial momentum zero. Final momentum should be zero. So therefore, they must have same velocity. So what actually happens, this is one sequence like that. This will go collide. In fact, this VC should be towards left. It should not be shown like this. I'll just put it. It is such a way that it will be. This will go and collide. This VC will be very much greater than VA. So VC3, I think we have VC3 only, let me keep it. VC3 will be very much greater than, let me have this one. So this will be VB3. Will be very much greater than VA1. VC3 will be very much greater than VB3. Again, it'll go and collapse. Like this, the sequence will occur, and finally, what we get is C will be at rest. Somewhere, we don't know. Okay, no. Why they must have same speed? VA equal to VB. Why they must have same speed? Conservation of momentum. Momentum conservation. So therefore, first I'll apply conservation of mechanical energy. Okay, getting this one. I think the mathematics, what is very important, that very much less than, without that, okay, whatever we want, we'll think it. So can be